Okay, I guess there's no one on Zoom. Thank you for coming. So this is the third part, the final part of my presentation. I hope to do as much as possible, but there's still plenty of stuff that we ought to discuss. So I'm going to do my best. So just to recall, we have two integers, two probabilities, and I'm looking at two shifts, full shifts, and these are called Bernoulli schemes, recall. And the claim is that if their entropy is the same, then there should be an Ash homeomorphism that conjugates them. Recall that this meant that there's a, so this is a partially defined function such that it is defined on a full measure set. And on that full measure set, with respect to the subspace topology, it becomes a homeomorphism onto its image that is also full measure. And of course, the other way around is straightforward. And this was the definition of entropy, Kolmogorov-Sinai entropy. So we have a bunch of different cases here. Okay, so now I'm starting really the proof. Of course, if A is 1, that means that the first system is trivial. And that means that in order, so the entropy ought to be 0. And the only way that can happen is the other one, the probability for the other one is also a delta measure. That is to say, only one of these components is 1. And so this row is okay, and this column is okay. In this case, based on straightforward, calculus arguments, you can realize that the entropy can be equal only when you have a homeomorphism that is defined everywhere. This is also straightforward. This next case is this part. That is to say, one of the symbols, one of the shifts have two symbols, the other one has more than two symbols. The argument that Keane-Smorodinsky give also work for this case, but you need to do some adjustments. So I'm just going to skip this case so that we're in this case. Okay. So assume A and B are at least 3. Okay. So the first step is using an argument that is, so it's based on, I guess it would be appropriate to call entropy flexibility for Bernoulli schemes. What you do is you take these two vectors, and the first step is to match one of their components. Lemma. There is a C, and there is a probability on it. Underscore, recall, meant the set with C elements, such that first of all, the entropy is the same. I'm assuming that the entropy of P and the entropy of Q are the same. Entropy is the same. There is some I such that R0 is equal to P0. Sorry, Pi. And then there's some J such that R1 equals 2J. So somehow this intermediate vector that you come up with has one component that coincides with some component of the first vector and some other component that corresponds with some component of the second vector. And so this comes from proof by entropy flexibility of Bernoulli schemes. And by this I mean that there's a straightforward argument that says that given any eta, you can find a Bernoulli scheme with that entropy. So whatever argument you use to verify this also gives you this. So based on this, we can say that up to a permutation, P0 and Q0 is the same. So based on this, from this, let me write it over there. Okay. So that is to say, the probability of occurrence of the zeroth symbol in X, the first space, is the same probability. Or at least I can assume this. And this zero symbol is going to be a marker for me. Okay. So because of this, 0 is going to be a marker. And I want to have my Ash homeo to, at the very least, take the 0 symbol to the 0 symbol. Or if you want the sequence that is all zeros to the sequence that is all zeros. And whenever you see in any point here a 0 in some component, you want the image to have the same 0 at the same place. So this sort of gives you something like a frame for your Ash homeomorphism. Okay, so this is the first step. Okay. So this also, you can realize, defines a common factor for the both systems. That is to say, if I were to say, for instance, O, this is going to be my marker, and you can imagine this to be a hug as well, and X, this is going to be everything else. So 0 symbol, I'm going to send to O. Every other symbol from either space, I'm going to send to X. In other words, KISS. So everything else. Okay, so this is a two symbol shift it's going to be, but so let me send A to KISS hug, 0 to O, else to X. And likewise, I'm going to do the same thing with B underscore 0 to O, everything else to X. Okay, so this induces factor maps from X to the shift, full shift on these two symbols, and likewise for Y. So this induces, let me write it here. This is P hat sigma X, Q hat sigma Y, and then a common factor. Let me call it just sigma. And then what's going to be the probability here is going to have two components, PO, which is going to be P0, and PXP KISS is 1 minus PO. And this is called the marker process. It's also, of course, just a Bernoulli scheme. But and this statement here means that I want to build my Ash homeomorphism here in a fiber-preserving manner. Okay? So this is step 1. Step 2 is to start building some combinatorial structures that allow you to handle the fibers. Essentially, you want you want some control over the fiber entropies. And the combinatorial structure that you use is what's called a skeleton. And it's just going to be a certain type of word in kisses and hugs. And then once you figure that out, and after proving a couple lemmas that tell you something about the sizes of certain sizes of sets that represent certain skeletons, you apply this structure, societies, etc., that we discussed last time to start building this phi one step at a time from one skeleton to the other. Let me define what a skeleton is. So the idea is always that you see, in the context of societies as well, you overcount first, but you just associate some set to any point, and then you sort of refine it to get a coupling. And it's sort of like the same idea. You always overcount, and then you reduce. This is the idea. So definition, let me take R and L, two integers, and I'm going to call skeleton of rank R and length L is, so skeleton S, is a word in kisses and hugs of this form, of the following form. I'm going to do something slightly different from what Keane-Smorodinsky do, but it's the same. It's equivalent. I start with a kiss. I have a bunch of hugs and then a bunch of kisses. Like this. So you alternate between, so you start with one kiss here and one kiss there, and in between you're alternating between sequences of hugs and kisses. So this I'm going to call the end hug, this too. And the middle sequences of hugs I'm going to call mid hug. And this is the end kiss, mid kisses. Anyway. In such a way that, and this is where the parameters come into play, the length of either end hug is at least R, and the sum of, so the total x's, total kisses, is exactly L. So in your skeleton, you have L, exactly L, spaces to be filled in. X marks places that you need to fill in. And hugs tell you, so you have sort of like a large sequence, initial sequence that tells you this is where my skeleton starts. And then in between, you still can have hugs, but it can only be less. So either end hug has to have at least R, and any mid hug cannot be longer or equal to R. And mid kiss equals L. Okay, you can write this in a more explicit manner as well, but let me just leave it like this. But it turns out that this is not quite sufficient. You want to be able to fast forward this a little bit. So instead of just leaving it like this, you say also, you take a sequence that goes to infinity, and then you call a skeleton S is an end rank R skeleton of length L if it's a rank n sub r length L skeleton. So R is an integer. I'm imagining this to go to infinity, 1, 2, 3, 4. And n sub r is also a sequence of integers that possibly go faster than r does to infinity. Okay? So examples. Rank 1, for instance, means that you don't have any mid-hugs. This is an example. So is this. And so on. But you could have n hugs larger than 1. If you wanted, you could have done this or this. Okay. All of these are words and kisses and hugs, and each of them is a rank 1 skeleton. This has length 1, length 2, length 3, 1, again 1, and so on. I should mention that the rank is not unique. So for instance, this is a rank 1, length 1 skeleton, but it's also a rank 2, length 1 skeleton. Okay? This is the idea. So the important thing about this is that you define these because if you were to see this block of code in your Word, if you were to shift this in any way, it would have empty intersection. So this gives you a very nice combinatorics. That's the first thing. And then the second thing is that if you were to increase R, if you were to start with a rank R skeleton, you would be able to decompose it uniquely into rank R minus 1 skeleton. Rank decomposition. And I'm just going to give a proof by example. Okay, so this is a rank 3 skeleton. I started with 3, as you see. I'm saying this is where my skeleton starts. This is where it ends. In the middle, I have hugs, but none of them have length 3. Okay. So now what is the rank 2? So rank 2 decomposition for this? Well, I can say this. This is 1, then 2, 3. That's the rank 2 decomposition. And then the rank 1 decomposition of this is this. This is still rank 1. But you see now I cannot go all the way because I have this. Now I would need to split it like this. Okay? This is the idea. So now a lemma that tells you some further things. Let me clear here. Okay. And so I'm going to say that I observe I observe a skeleton in a word in an actual point in X. If I see a part of my point in X that is fitting into this skeleton. So this means that, for instance, so let's say that x is like this. So let's say 0, 1, 2, 0, and then this is also 2, and then you have 0 here. I'm just looking at the finite block of it, and then the associated skeleton for this would be hug, kiss, kiss, hug. Of course, it has a growing sequence of skeleta that fit into each other. In this case, there is more than one skeleton that x fits into, or that fits into x. But if your 0th entry were not the marker symbol, then there would be a unique skeleton for any rank. Let me write this. Let me write it like this. For almost all x in x. Yes.
Can you let x interpret
That's good.
But also the elements.
It's small. It's small.
But it's also kiss, right?
Yes, but it's large. I mean, I could have done zeros and ones, so I decided to do this. Yeah, P. Well, omega. Okay. For almost every word, almost every sequence in omega, for any integer sequence that goes to infinity, and for any r, there is an n rank r skeleton that's denoted by S sub nr of x. And if the zeroth coordinate of omega is not 0, then this is unique.
And you're insisting that the 0 coordinate is one of your islands?
No, that's why. So if the 0th coordinate is 0, there are many skeleta that you can put in, because it just hits into one of the markers, and you're not controlling the markers at this point. But if it's not 0, then you just sort of start reading your word to the left and to the right, and you're counting, then you're switching to markers and hugs and kisses. And based on that, it is sort of, and once you fix the rank as well, it gives you the unique skeleton. If not, then there are multiple. So yeah. So okay, this is the first one. And then the second is that for all, I'm going to normal text. Okay. For all sequences that go to infinity, and this is going to be the second parameter. This is going to be the length parameter, if you want. And for all n that go to infinity, for all omega in omega, there is an R naught such that for all R larger than R naught, Sorry, I don't have this actually. For all length sequences, for all rank sequences, there is some large enough R such that after that, if you were to look at the skeleton, such that its length is at least R, this has full measure. Okay. Yeah. Okay. Oh, sorry, this should be there exists. If I fix a length sequence, I can find a rank sequence, so I can fast forward my skeleton such that for large enough parts of the system of skeleton, I have that the unique skeleton has length at least L sub R. So for almost all points. Okay, so these two are going to be the parameters. And the idea, let me say, is that so from something else, we're going to get this, what this L should be, and that something else is going to be the Shannon-Macmillan-Bryman theorem. And once you have this, it's going to tell you the increasing rank sequence that you should be using. Okay, so this is that. And this is just Borel-Cantelli. This is by Borel-Cantelli. Right, so this is what is this? This is a lim-inf really, lim-inf of these sets. I'm taking the lim-inf. You can just show that one of them has, or the complement of one of them, for large for large R is 0, etc. So straightforward measure theory arguments. Okay. So this is the skeleton that we're going to be using. And the next up is the fillers. You don't touch hugs, and you're trying to figure out, so once you have a skeleton like this is where this method shines, I think. Because this also can be interpreted as a couple of cylinders of the marker process of the common factor, you can also interpret this as telling you something about the first system, omega, and the second system, y. And so this is where this is why this is useful. You said that, so you're saying that my Ash homeomorphism should preserve the hugs. Okay, so now you have these spaces that you need to fill in. Once you have this in the first system, based on some arguments, you need to figure out where to send it. And this is where the idea of the society comes into play. But before going into that even, let me just say a couple more words. So I can interpret my probability vector to be a point in the simplex. And so now let me define a new probability on the set that contains everything but the marker. Okay? So this is just P0I is going to be Pi divided by 1 minus P0. Let's assume that P0 is not 0, is not 1. So geometrically speaking, if this is my simplex of probabilities, and if, let me just draw it like this. If your probability is here, you look at the projection here, and then you extend it so that you get another probability. So if this were P, this were P naught. Okay? And so this is called the filler alphabet. Filler probability. And likewise, its H is the filler entropy. That's to say fiber, if you want. Fiber entropy. Okay? So now you see this entropy too is going to be matching. So H of P0 is going to be the same thing as H of Q0. Because of our assumption that the zeroth component of P is the same thing as the zero component of Q. So they're going to have, the fillers are going to be also the same. Okay, so now, now we need more combinatorics. Okay. I don't think I'm going to do a good job explaining this next part. So I'm going to have S a skeleton. Let me denote by F to the omega of S the fillers of coming from omega. That is to say, this is a certain set of finite words, and the symbols coming from here, where you put them into the spaces of x's. Okay, coming from. Let me just write it like this: fillers of S coming from so take symbols from the filler alphabet. A underscore take away 0. Put them in x's. So it is bijective with with a set of words. So this is the length of the skeleton into A underscore take away 0. It is bijective, but given the skeleton, its hugs are at certain places. So in a sense, because you're attaching this to the skeleton, you're encoding a place information as well. But it's a finite set. It's a finite set of words in the filler alphabet. Okay. So now I want to define an equivalence relation on it. And the way you do this is by a certain, so if you have a set of words, and if you want to define an equivalence relation on it, one way to do this, a more straightforward way of doing this, would be to say, I'm just going to look at certain places, and I'm going to say two fillers are the same if they are the same at those places. So if their restrictions are the same. Okay, so that's a standard way of defining an equivalence relation on a set of words. Where you should be looking at is going to be dependent on the entropies. And so that's going to, for that, you're going to need something like a stopping time. And because of that, so this is exactly where the Shannon-Macmillan-Brightman comes into play. Okay. You want to define an equivalence relation on this, and as well as on f to the y of s. Say you have a subset J of S of, oh, this should be, let's say, over. So this is a set with L of S elements. In this set, and put F1, F2, two fillers, two words. If, first of all, oh, sorry, this should be a filler. Say, for all F, for any filler, you have a certain place or subset of your indexing set. If, first of all, the indexing sets are the same, and if I were to restrict either one of these fillers to this indexing set, let me just call it J, on it, they're the same. So I can imagine a word to be a function from this finite set as well. I'm saying two functions are going to be equivalent if there is a certain subset in their domain such that on it, when you restrict both of the functions onto that subset, they are the same function. This is how you define it, and it turns out that, so we're going to figure out what this subset is based on entropy considerations. Comes from entropy considerations. Considerations. You actually start with the first element, right? So let me just write this explicitly. For any filler, J is fixed.
And you're going to tell us how to use it later?
Yes, I'm actually going to do it now. Say, for any filler, there is a J. So this set is this. So this is how you define J of F. You take your filler, okay? Let me give an example, perhaps. It's going to be better. Erase this. you take your filler. So I can imagine this to be something like this. F equals F1, F2, dot, 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 F also this. Each of these is a filler symbol, and they're ordered. And the fact that this is a filler for S means that if S were kiss, hug, hug, kiss, kiss, etc., means that I'm putting the first symbol to the first kiss, second symbol here, last symbol to the last kiss that is in the middle. Okay? Start reading off from the left these symbols. And you sort of keep taking more indices insofar as their measure is not below a certain threshold. So fix, let me say it this way. Fix and epsilon sub r positive, tilde, epsilon sub r tilde positive. And say that J sub f is the set of all those entries or all those indices I in my index set, such that if I were to use the filler probability, let me write it like this. So here's the thing. So I'm looking at the probability of this symbol, okay, with respect to P0, my filler probability. And then I'm saying, is this larger than, more or less than this epsilon? If it is, then I keep going. I take another one. Now, all of these probabilities are less than 1, which means that it keeps decreasing, or it's not increasing. And eventually, you're gonna be lesser than this. But until you get to that threshold, you keep taking more indices. Okay, that's the idea. Let me be more explicit here. Let me just write it like this. So P0 of F1, P0 of F2, P0 of Fi is not lesser than my threshold. Okay? So there's going to be a maximum here. You're going to have a maximum index such that all the previous indices are here. Okay? So you're just taking the first part of your filler. However much, that depends on this filler probabilities. Where does this come into play? Or where do you get that epsilon r? Well, you get it from Shannon McNeil-Ryman. Okay? So, I mean, this still defines an equivalence relation, but it's just that it doesn't, that equivalence relation doesn't necessarily work for our purposes. And of course, the equivalence relation here that I defined is going to be dependent on what this number is. And R is the rank of the skeleton. Okay. Okay, I have 13 minutes. I want to mention, where does this epsilon sub r comes into play? Because I want to be able to do this in such a way that as I'm increasing r, because of that r is the index of my length sequence or the rank sequence n. And so as I'm increasing it, that sort of represents taking larger and larger skeleta that fit into each other in such a way that if I were to look at the larger skeleton, it has unique sort of smaller subskeleton based on this decomposition that we discussed. So I'm just going to state a certain version of SMB theorem. And I think this is called the, what is it called? Entropy equipartition. Yeah, entropy equipartition property. Okay. So, let me just state it generally. If you have an ergodic system, there's an arbitrary x, m, ergodic. And let's say that its entropy is finite. We discussed a little bit last time at the end how this entropy can be interpreted as the average of a certain information function. Well, in a sense, this is just telling you that you have pointwise convergence. Let me be more explicit. So here I'm going to denote by, so let's have alpha be a finite partition, be a generating partition, generating partition. Recall by Krieger, because entropy is finite, this exists. Which means that if I were to take this and if I were to refine it using its images under F, I would get the whole sigma algebra. Then for all epsilon, there is an n for all n larger than n. This refined partition up to time n. So this is up to time n of alpha. This just means alpha refine, pull back, refine x squared all the way up to n minus 1. If you want, this is a cocycle over the pullback operator on the space of partitions. So this is split into two categories. So let me write it like this. It is a good part and a bad part. This is bad. And of course, it depends on epsilon, n, and f. Let me not write those. In such a way that the bad part, so the total measure that is covered by elements in the bad part, is less than epsilon. And if I were to take any cell in the good part, its measure is comparable to e to the entropy up to time n. This is just a lower level statement of what I just said before. It's a certain entropy, so it's just saying that a certain information function is converging pointwise almost everywhere. Such that mu of the union of all those bad cells is less than epsilon. And for all cells in the good part, so the measure of the cell is bounded from above and below by e to the minus n entropy minus epsilon in here. Minus n and f plus epsilon. Okay. Of course, in information theory, we put here a 2, but I'm counting entropy in nats instead of bits, so I'm using e. Okay. So how do you use this? Well, you have a sequence R that goes to infinity. For each R, I'm going to do something. Yeah. So now fix. Okay, so I'm just going to use this equipartition property. Okay, so of a small measure set, I have a nice partition given by refining the generating partition using my dynamics. The measure of my cell, or of any cell, is proportional to n times entropy, logarithmically speaking. This is also telling you why entropy formulas should be true, actually. So now take a sequence that goes to 0, parameterized by R, let's say, and let alpha be the standard generating partition of 0 cylinders, be the generating partition. For the filler system. Something start. Okay. Then for all R, there is a time k sub n sub r, such that for all n after that time, or maybe I should have used k actually. Let me just use k to be safe. For all k, if I were to look at the refined partition, splits into a good part and a bad part, such that the bad part has measure at most epsilon sub r, and for all g in the good part, this is bounded from above and below by so minus k entropy of the filler minus epsilon in here, e to the k entropy of the filler plus epsilon. And essentially, this is epsilon sub r, and this is my stopping time. Okay. So, and of course, these partitions, as you see, I'm taking a finite refinement of my standard cylinder, which means that I'm just taking a block code that is finite, and I'm saying that of a small measure subset of block codes, I have this very nice estimate. But of course, these can be interpreted as things that as something that tells you something about the fillers as well. Eventually, you're going to possibly fall under this bound, or this bound, whatever. And based on this, now if you were to define equivalences, so the equivalence relation between two fillers using this bound, it works. Okay, this is the idea. 2 minutes. Okay. So we have now a machinery. Okay. We have a sequence epsilon dot that goes to 0. Based on this, we have another sequence epsilon sub r, or epsilon dot tilde, that also goes to 0, but in a way that is compatible with entropy. Given by this. Now from this, recall that in the skeleton lemma, or lemma about skeleton, we had something that said, based on an increasing length sequence, I have an increasing rank sequence. Well, I'm going to choose that length sequence to increase in such a way that is compatible with the decrease here. And this is how you find the parameters that you should be using. Okay? So, okay, I'm running out of time. Let me just say one final thing as to how this matching works. You start with a skeleton. It has its filler set, its equivalence relations, everything. You write it, this is rank n r. You write it as, I'll just write it like this, is 2 as skeleton of rank 1 less. Okay, and so now inductively, you can compare the equivalence relation here and each of these equivalence relations put together. So one of them is coarser than the other one, but based on which one is more coarser, which I'm going to mess up, that's why I'm not saying, based on which one is more coarser, you're defining, so from this, you get a society. Okay? From the fillers of omega with respect to S, or rather up to sigma, up to tilde, to the fillers of the other guy. Then you apply marriage lemma to get a coupling from this, like we discussed last week. And when your R is odd, you go one way. When your R is even, you go the other way. And so this sort of allows you to basically zip the two dynamics together along the fibers. I wish I could say more, but I think this is all I want to say today. And this is the end. Thank you.